All right. So let's get started with the class. Today we'll start a new topic. Remember last time we talked about replication, and before that we talked about caching, consistency, and related topics. So we are going to switch gears and talk about the other benefit of replication, which is fault tolerance. Okay. Essentially, when you have a system where the chances of failures are high, you want to ensure that the failure of one or even more than one component does not bring down your entire system, especially in larger distributed systems. That's an important property you want to have. So what we'll do today is talk about high-level concepts on fault tolerance, some terminology. Then I'm going to introduce this notion of crash fault tolerance and Byzantine fault tolerance. Okay, and then we will talk a little bit about reliable communication. We said some stuff about this earlier on in this course, but I will maybe add a little bit from the fault tolerance perspective. We'll talk about distributed commit. We may or may not finish both of those aspects of distributed commit, which is two-phase and three-phase commit, but at least I hope we'll start today. Okay. Next time we are going to continue that discussion, talk about consensus. We'll talk about the Paxos protocol. We'll talk about Raft, which is a version of Paxos. Talk a little bit about how to recover from failures. Okay, so all of this is to prevent failures in the first place, but suppose you had them anyway, how do you recover from it? Okay, so that's going to be the agenda for the fault tolerance part of the course. Okay, so let's start with the basics. I mentioned a little bit of this last time, but let me repeat some of this. Okay, so essentially, when you have single machine systems or centralized systems, if there is a crash, hardware crash, the machine fails, or the OS crash, the machine also fails, or disk crashes, then essentially your entire application that's running on the machine is going to stop. Okay? Now, in a distributed system, there are multiple nodes that are interconnected. Okay? So even if one node fails, okay, the system as a whole, there are other nodes that are still operational. So what you want is a way by which you can tolerate the failure of some number of nodes and yet keep the system running. That's not even an option when you have a single machine system. But here, at least, we can think about how can partial failures be tolerated, okay, if some nodes fail. Okay? And then the question is, how do you then recover from them and so on. Okay? And last time I talked about this thing at the very bottom, which is what is the probability of failure in a system. Okay? Let's say that you have n nodes, n components in a system, and each of them can fail with some probability p. Okay? So the probability that there is a failure in the system, okay, is essentially the probability that there is any one or more systems of components have failed, okay, which essentially is the probability of having no failures in the system. So essentially, probability of a failure, okay, is essentially 1 minus the probability of no failure, which is essentially it's going to look like something like this. So as you can see, n is the number of components in the system. As n grows large, this term is going to become smaller and smaller because p is essentially a term that is less than 1 numerically. Okay? So the probability that some component has failed in the system will start approaching 1. Okay? And that's by and large true in large systems. The larger your system, a failure of some components becomes the common case. There's at least some server or some small number of servers that essentially have gone down, etc. Okay? So the probability is going to approach 1, which means that in a distributed system, okay, you will not have to take this into account. You want to ensure that there are ways to tolerate these failures. Okay, all right. So what can we do? Okay, so let's think about some perspectives here. Okay, the first thing is computing systems not very reliable. Okay, we are used to things crashing all the time. Okay, your machine may crash, your application may crash. Okay, as computer scientists, we have encountered these software failures, so we have a higher tolerance for them. Okay, we reboot our system, we restart our phones, we relaunch the application, and so on. Okay? But that's for more the tech savvy users. Now, computing is everywhere. So you have to now think about how other users who are not technologically savvy are going to deal with this. Okay? So if you tell people that, okay, this TV is now essentially running an operating systems, every 2 days is going to crash, you have to restart it. People are not used to this type of operation. Okay, they expect things to just work. Okay, they don't expect that software is inherently buggy, so you got to reboot it and things of that sort. Okay, so you don't want to tell people to keep rebooting their TV because it froze and now it's something has crashed on it and so on. So in some sense, as computing has become more pervasive, okay, and these are all examples of distributed systems because all these devices also talk to one another, we need to make things more reliable. Okay, and now as people also rely on these systems for doing their banking or buying things from the internet or trading or sending email, you also now don't expect the system, or not don't expect, don't want the system to fail because you are relying on it for day-to-day activity. Okay, so you want to build more reliable or what is called dependable system. Okay, so essentially there are some terms that are used in the context of dependability. One is availability. Availability essentially means that the system should be available for use at any given time, and the availability of the system is measured simply in terms of a percentage. Okay, so you essentially have high availability systems could say you are 99% available, which means you are available for 99% of the time. Okay, you can be 99.9% available and so on. Okay, so depending on how reliable the system is. Okay, so first of all, if the system is not reliable, it won't be even close to 99%, maybe 70% reliable. Those are not good examples, but let's say there are systems that have been built to be highly available. You measure their availabilities in terms of what is called the number of nines in its reliability metric. So some system that's 99.999% reliable, also called 5 nines of reliability because there are 5 nines in that term. Okay, so and then you can have 4 nines of reliability, which just means 99.99, or 2 nines of reliability just mean 99% reliable. Now I just wanted to put some numbers here so you can understand what this actually means in practice. Okay, so if you have 5 nines of reliability, which is 99.999%, that means that the system can be down no more than 5.26 minutes a year. Okay, very high level of reliability. You can't afford to have much downtime at all. Okay, 4 nines is 56 minutes a year. Okay, when you get to 2 nines, that means you can be down 3.5 days a year. Okay, so any of these systems, even 2 nines is actually not that easy to achieve because any number of things keep going wrong in large systems and things fail and whatnot. Okay, now 5 nines is considered to be really good. Okay, very few systems actually achieve that, but that's what many systems aspire to do. Okay, but if you get anywhere close to any number of nines, that's actually good. Yeah, for many systems. Okay, so that's availability. Reliability essentially says that the system should run continuously without a failure. Okay, different terms, slightly different from availability. Okay, safety means that any single component failure should not cause cascading failures and bring the entire system down. Okay, so that's safety. So essentially, if your computing systems that are designed for, let's say, controlling an airplane or nuclear reactors, these need to have high safety guarantees. You don't want some component failing to cause catastrophic failure, okay, because maybe people's lives depend on it and so on. Okay, maintainability says that failed system should be easy to repair. Okay, so it should be built in a way that allows it to be easy to repair. Okay, and then there are what types of failures can occur, and we'll go through a taxonomy on the next slide. But I want to mention 3 types of failures here. Transient failure means it essentially is a one-time. There's some problem and it goes away by itself or for any reason. Okay, so that's transient. Intermittent may essentially means that the system fails for some period of time and then it gets better and then it works fine for some other period of time, then there's another intermittent fault and so on. Okay, and then your permanent failure, which means actually fails and doesn't recover from a failure. Okay, so I'm going to focus on permanent failures for the large part in the next few slides. When we get to Byzantine failures, then all of these concepts get covered under. Okay, so here are some types of permanent failure. Okay, crash failure is the simplest one. System just crashed; it doesn't work. Okay, that's a very simple type of failure. Okay, omission failure essentially says that a server is up, but it is not responding to requests. Okay, that's an omission failure. Timing failure essentially says that it is responding, but it's really slow. So its time to respond is very long. Okay, not tolerable for most use cases. Okay. Response failure essentially says that it's producing some response that is incorrect. Okay, and then you essentially have some arbitrary failures, which means that it can do arbitrary things at arbitrary times. Sometimes it doesn't respond, sometimes it responds incorrectly, and so on. Okay, so different kinds of failures. We'll start with the simplest one, which is crash failures. Then we'll get to essentially the last one, arbitrary failures, which are also called Byzantine faults, okay, Byzantine failures. Okay, any questions on this? Okay, so here is an example of how you can use replication to get fault tolerance, to tolerate some number of failures. So here we can assume crash failures. Okay, and so here you have a circuit at the top. It has three components, A, B, and C. That's an electronic circuit, not a program at this point. So you assume that you can send an input to A, it does some computation, it produces an output that's fed to B, that produces an output, and that is fed to C. Okay, so essentially what happens in this case is if A, B, or C, any of them fail, the system as a whole has gone down. It doesn't work. Right? The circuit has failed. So what can you do? So what's shown in the bottom is a replicated version of that circuit where you have 3 copies of component A, okay, 3 copies of component B, and 3 copies of component C. Okay, so now what this means is, and you also have put what is called a voter. Okay, what the goal of the voter is essentially to take the inputs and pass the majority in output out. Okay, so that's essentially what's going to happen. So each voter is going to take inputs from all 3 components and take the majority vote. So if the one component has failed and it's producing some bad values, okay, then you can essentially have the other 2 components will agree, and this voter will then pick the majority value and then pass it on. Okay, so now if A2 has failed or is producing bad values, okay, A1 and A3 are doing the right thing. The voter 1 is going to get values from A1, A2, A3. One of them is bad, 2 are right. The majority vote essentially takes the correct value and outputs it. And that's what gets fed to B1, and the same thing with B2 and 1. Okay, so essentially you are using replication and a voter that's essentially asking all the replicas to produce an answer. Okay, you take the majority answer. In this case, okay, you can have one component failing, the other 2 will produce the right answer, so you know which is right, okay, and then you pass it along. Okay, so is that clear? Okay. This is called triple modular redundancy, or TMR, where every component is replicated 3 times, okay, to tolerate failures. Okay. Now you might also see that the voter stage at each level is also replicated 3 times. Okay. So you may ask, why is that the case? Why couldn't you have just put one voter, all 3 versions of A feed that voter, all 3 versions of B feed their voter, and so on? Okay. Why do we need to have 3 of these? Okay. You need 3 of A, B, and C, because though that's the original circuit. Why do you need a voter to be replicated? Okay. The voter could have the same problem. There is no guarantee that the components are right, or the voter is always right, only the components are failing. So since any component can fail, okay, you want to make sure that any additional component you add also has the 3 levels of redundancy. Otherwise, that becomes a single point of failure in your system. And then if that component fails, then the system is not going to work as you intended. Okay, this is a simple example. This is what is used in electronic circuits if you want to have a high degree of redundancy. But this example is going to give us some ideas on how we are going to develop distributed systems in a similar manner. So we are going to replicate components, and then we are going to essentially figure out which components work, which ones don't work, using some form of voting to see what is the right answer that the component should produce for any request. Okay. So with that very simple example, let's get into a little bit of details here. So we'll first start with what is called crash fault tolerance. A system is just crashed. Okay, so it either produces the right output when it's functioning, or it produces no output when it has crashed. Okay, it's not producing bad outputs. Okay, it's either when it runs it runs correctly, or when it fails, it doesn't work at all. Okay, so that's essentially called crash fault tolerance. Okay. Now, if you want to deal with crash fault tolerance, and specifically you want to tolerate up to k crashes all at once. Okay. K can be any number. If k is 1, that means it's one fault tolerance. You can tolerate one failure at any time. If you want to do 2 fault tolerance, that means up to 2 components can fail simultaneously. Okay. So you can have k fault tolerance. Okay. So to do this, you need to have k plus 1 redundant copies. Okay. Because up to k can fail. Okay. And the ones that are running are producing the right result. So no voting is needed in this case, because whatever is working is producing the right result. So if you want to tolerate k fault, you have to have k plus 1 copies, because even with k fault, there's at least one functioning copy that's going to give us the right result. Okay. So crash fault tolerance is the easy case. Okay. You just need one more copy than the number of faults you want to tolerate, and you are done, because we are not assuming that the component is producing bad results. It just doesn't produce any result. So you know it has failed because it's not responding. Okay. So that's crash fault tolerance. Okay. Now, the more complicated case is what is called Byzantine fault tolerance. Okay. And here, what happens is processes can run even if they have faults, and they can now produce arbitrary result, which means that you feed it an input, you give it a request, what the response it produces cannot be trusted, because it may be right, it may be wrong. It produced a response, you just don't know. Okay. So these kinds of faults are much harder to deal with. Okay. And then the question is, how many replicas are you going to put in this case? Okay. It can't be k plus 1, because you can have arbitrary output that are produced by k. Okay. If all k of them produce the same incorrect response and you use voting, you are going to it's not going to work at all. Okay. Because you will take all the k bad responses and they all agree, so you will think that's the actual response, but that's not really the case. So you need a lot more replicas than k plus 1 in case of tolerating Byzantine faults. Is that clear? What I just said, I haven't said how many you need, but at least it should be clear that this is a harder case for us. Question, yes. Question is, the redundancy example that we looked at, is that for Byzantine or not? So you can do Byzantine with this one. Crashes are actually easy. Okay? If you do crash, then you can tolerate 2, right? Because the third one will produce the output. That 2 have just failed; they don't produce any output. But you can essentially do Byzantine as well. Okay. All right. So let's start thinking about how are we going to deal with Byzantine faults. We'll start with a simple example, then we'll make a more complicated one, and so on. So we'll think about 2 processes, okay, that are communicating with one another. But in this case, we are not going to assume the processes are faulty, okay, but the network is faulty. Okay? Network is Byzantine faulty. Okay, you send a message. Okay, there are 2 processes, A and B. A sends a message to B. What arrives at the other end, you cannot actually trust, because the network can deliver the correct message. It can not deliver any message. It can change the message and deliver an incorrect message. Network is capable of doing anything it needs to. It can. Okay? The question is, how can A and B actually agree on something by sending messages? Okay? So we'll construct a real world example, which is called the Byzantine's general problem, okay? And try to think about how you will do this. Okay? So assume that there are 2 armies that are trying to attack a common adversary. Okay, the armies need to figure out what time to coordinate the attack. Okay, so the way they are going to figure this out is the generals are going to send a messenger which is going to carry a message saying let's attack at 8 a.m. or something like that. Okay, and you want to now make sure that both armies have actually received this message and agreed that that's the time they are going to launch an attack. Okay, now we will assume that the messenger goes through some hostile territory. Okay, that's equivalent to our network. The two armies are our two processes in this case. Okay, so the messenger goes in hostile territory, so anything can happen to the messenger. Okay, messenger may get captured. Okay, the adversary can capture the messenger and send a different messenger with a bad message. So anything is possible. Okay, so it's almost like a real world example when two armies are trying to coordinate. Okay, so now the question is, how can we ensure that the two armies actually agree on what time you want to launch the attack? Is that clear? Okay, so we'll assume that these two armies, will call them A and B. Okay, A is going to send off a messenger saying let's attack at 8 a.m. Okay, for now let's assume the messenger has actually reached the other end without getting intercepted or anything like that. So the message actually gets delivered. Okay, so the other end knows that what time A wants to attack. Okay, are we done? No. Okay, why are we not done? Sorry, somebody said. Okay, so you don't know, you send the messenger actually reached the other end, but you don't know the messenger reached. Right? How do you know the messenger has actually reached? Messenger could have been intercepted in transit. Okay, so let's say, so at least we know that this is not enough, okay? Because you don't know whether your message has reached or not. So you might say, okay, let's get an acknowledgement. Let's send the messenger back saying, yes, I received your message. Okay. So now again, let's assume, of course, if the messenger gets captured and the message never reaches, then the problem is not solved. But just for simplicity, let's say the messenger actually makes it back. Okay, you sent a message saying let's attack. Message was received. Okay, you got a reply saying yes, message is received. Okay, are we done now? Yes. Okay. Okay, so message could have been corrupted. Okay, you get some message back, you don't know. Okay, that's the more devious case. Let's say the messenger never got to the other end, got intercepted, but a fake messenger came back and said message received. Okay, so that clearly you cannot trust. But I'm just asking a simpler question. Let's say that the message is not corrupted yet. The messenger went to the other end, okay, delivered the message, came back with acknowledgement, you got the acknowledgement. Do the two generals or armies have agreement? No. Okay, why not? Okay, then now we have the opposite problem, that the message has come back, but the receiver doesn't know that your message has come back. So so they don't know that your whatever you said has gone back or not. Okay, is that clear? Okay, so what do? You can send an acknowledgement to the acknowledgement. Yeah, the messenger is going to get a lot of miles. Messenger goes back saying, okay, I delivered your acknowledgement. Okay, and maybe you actually reach the other end. Okay, now you sent an acknowledgement, you can send an acknowledgement to the acknowledgement. Now what? Okay, so it's still no agreement, because you never know, whoever is sending the message actually never knows whether the message has gotten to the other end, because the territory is hostile. Okay, so no matter how many acknowledgements you send saying, yes, I received your message and I received the acknowledgement, I received the acknowledgement to the acknowledgement, you are not going to reach agreement simply because you never know whether the last message that was sent has actually been delivered. Okay, it may not be. Okay, that's the easy case. Of course, we have the harder case where message could be actually altered. Okay, instead of saying let's attack at 8, you might have altered the message and let's attack at 9. So that's the harder problem. So I'm not even gotten that far. Okay, I'm saying that even when messages are actually being delivered, because there's a chance that the message cannot be delivered, that itself does not lead to any agreement. Okay, so you can have an infinite number of acknowledgements go back and forth, but you will never reach agreement. Okay, so that's a property that two perfect processes can never reach agreement or agree on something if the network is unreliable, because you will basically keep sending acknowledgements and you never know if it's ever been reached, if delivered or not. Okay, so this problem is also called reaching common knowledge. Common knowledge means that you know something, you know that everyone else knows something, and everyone knows that this is now known to every other party in the system. Okay, that means it has become common knowledge. So the two armies are trying to reach common knowledge or common ground on when you want to launch an attack, but they are not able to. They're not able to reach agreement. Okay, that's a property. There's nothing you can do about this. Right? So, so that's the two generals problem with a unreliable network. So now we'll say that so that problem can't be solved. Let's assume network is reliable. Okay, so now we'll assume that's not the problem, but let's assume that one of the generals is actually a traitor. So you can trust the network, but you may not be able to trust the generals. Okay, in particular, we'll now not have 2, but we'll have n generals. Okay, someone is a traitor. Okay, they are planting fake messages, but you want to agree on what time to launch an attack. Okay, the question is, can we solve that problem? At least we know that the network is faulty. We can't do it. Okay, now we'll assume network is not faulty. Processes might be faulty. They might produce garbage output. In this case, the generals are planting bad messages. They might deliver messages, etc. But we want to reach agreement. Okay, is that clear what the question is? Okay, so this is called the Byzantine generals problem. Okay, yes. Yes. So question is, what does it mean to see if the network is reliable? Okay. So it essentially means that your messages are delivered and the messages are delivered correctly. Okay. So we'll assume TCP can do that for us. Okay. TCP gets acknowledgements. It ensures that packets are not corrupted in transit and so on. So let's just assume TCP for now. Okay, so message delivery is solved, but we don't know whether the generals are to be trusted or not. Okay, so here is an example of a protocol that we can use to figure out how to reach agreement and also isolate the traitor in the process. Okay, because you have to do two things. You have to first decide what time to coordinate the attack. Okay, that was the goal. Okay, but you don't know who to trust, who not to trust. Somehow you have to figure out who are the trustworthy generals in the process. Otherwise, you don't know whose message to trust and whose message not to trust. So you can't reach agreement. Okay, so here's the way where we're going to essentially do a 2-round process. Okay, there are 4 generals, 1, 2, 3, and 4. Okay, 3 is the faulty general or the traitor. Okay, now the other generals don't know this. We know this. Okay? So it's not we, but the other generals have to figure this out and reach agreement. Okay, so here's what they are going to do. Okay, so in round 1, each of them is going to send a message saying, let's, in this case, doesn't matter what the message is, just have to agree on it. So we'll just assume that 1 is going to send 1, 2 is going to send 2, just so that you know who sent the message. Okay, the message could be, let's all agree to attack at noon, or it could be, here is the number of soldiers I have, something that you want to exchange and reach agreement. Okay, so in the first round, each general is going to send the same message to all other 3 generals. Okay, except for the traitor, who can send any arbitrary message. Okay, you can send the same message, which is bad. You can send some different message. So the other three generals can get three other messages from three or the same message. We don't know what it will send. So we'll just call that message X, Y, and Z because the message is not known a priori. Okay? So at the end of round one, okay, the general one is going to get one from itself, is going to get message 2 from 2, is going to get some arbitrary message X from 3, is going to get 4 from 4. Okay, and 2 is going to get 1, 2, Y, 4. 3 is gets the right message, but it's sending the wrong ones, and 4 gets 1, 2, Z, and 4. Okay, so at this point you don't know what to believe and what not to. You just gotten some messages. Okay, but now we are going to repeat recursively. We'll say take all the messages you received, which are these things, okay, and then send them back to everyone else. Is that clear? First round, you essentially send a message, okay, and then you collect all the messages you receive, and you said this is what I received previously. Okay, so you're going to send that. Okay, so you are going to now essentially this is what you'll see at the end of the second round. So 1 is going to essentially get 1, so it's going to get these other 3 messages. 1, 2, Y4 from 2 is going to get A, B, C, D from 3, because 3 can send any arbitrary thing, is going to get 1, 2, Z4. Okay, is that clear? Okay. And 2 is going to get something similar. So what it gets from 3 cannot be trusted, but what it gets from 1 and 4 is fine. When 4 essentially can get anything from 3, but what it gets from 1 and 2 is right. Okay. So now if you examine these messages, you will see that each of the generals who's not a traitor sees that the other 2 that are sending the right messages can be identified because there is a row and a column where they're agreeing. So it says, so you can see that 3 is sending bad messages because what everyone has received from 3 and what 3 has sent you is not matching. So you can assume that 3 is the faulty process because it's sending garbage, and you told everyone what 3 sent you, so that everyone knows what you got from 3 and what 3 sent to everyone else. So you can now identify that 3 is sending bad messages. Okay? But the other 2 are actually agreeing on what you get. So in case of 1, you will see that 2 and 4, they actually agree on what they received in the previous round. You can verify that that's the same thing I received, essentially. Right? That clear? So now in this case, you can essentially identify that 3 is faulty, it's sending bad messages, and you can essentially know who are the other 2 processes in the system that are getting the right messages. Any questions on this? Okay. This is also a technique that Lamport developed. It's called the recursive Byzantine general problem. Yes, John.
Process didn't fail if traders outnumber the loyalists.
The question is, does it fail if the traitors outnumber the process? Yes, it will fail. I'll show you in the next. Yes, indeed. Any questions here? Okay, so we'll repeat this with 3 rather than 4 and see what happens. Okay, same thing. Okay, there's one bad traitor. Here there are 2 good ones. Okay, only 1 and 2 are good, 3 are bad. Of course, there's the 1 and 2 don't know who's good and who's bad. Okay, so we'll do the same thing in round 1. You will essentially send 1, 2, and whatever 3 sends arbitrary messages. So 1 is going to get 1, 2, and X. Okay, 2 is going to get 1, 2, Y. 3 is going to get the right message. Okay, then you take this and you send it back. Okay, so now 1 gets 1, 2, Y from 2 and ABC from 3. Okay, so it can see that the 2 other processes or 2 generals are saying that they got different information from the others. Okay, so the 2 don't match. So you know something is wrong. Okay, but you don't know who to trust. Okay, because they are just 2 different messages. You can't distinguish which one is right and which one is not right in this case. Okay, and the same is the case at 2. Okay, it's going to get 1, 2, X at DF. So here you know that something is wrong. So identified there is a fault. There's a faulty process, but you can't isolate the fault because you don't know who is the right process and which one is the traitor. Is that clear? Okay? It's like you have two friends, one of them is lying, you just ask them something, they say two contradictory things, you don't know who to trust. Okay? So as simple as that. Here you have two processes that are telling you two different things, you don't know who to trust. If there are three, two of the three will at least agree because there are two good ones and one bad ones. But if there are just two and one of them is lying, you can't distinguish. Okay, is that clear? So to answer the question that was just raised, so you can't solve the problem if there are three processes and one of them is faulty, but you can solve it if there are four processes and one of them is faulty. Okay, so that can be generalized to a property that says that if there are m faulty processes, okay, and m Byzantine faulty processes, you need 3m plus 1 total replicas. Okay, we did the example with m equals 1. Okay, and there's one faulty process, you need 3m plus 1, which is 4 processes total in the system. So the degree of replication to tolerate one Byzantine fault is 4. You need 4 replicas just to tolerate one fault. Okay. When we had crash fault tolerance, yes, remember I said it's k plus 1 replica. So if you set that to 1, you need 2 replicas to tolerate one fault. One of them goes down, the other one works. Okay, that's crash fault tolerance. Here, one of them is bad, you need 4 total, so that there are 3 that are working well. Okay, so in some sense, you need 2/3 of the processes to work correctly for all of this to work. Okay, so what this should tell you is Byzantine fault tolerance needs a high degree of redundancy. Okay, to tolerate one component failing, you have to have 4 copies running. Okay, that's going to increase all your costs by 4x. You can't run just one copy. You have to run essentially get 4 servers, run 4 replicas. Okay, so to run one application, you essentially quadrupled your cost. Okay, so as opposed to crash fault tolerance, if you want to tolerate one fault, just have backup, a second copy running, and it works fine. So that's degree of replication is much lower. Okay, the hardware cost to do this is also much. Okay. So Byzantine fault tolerance, we know how to handle it, but because of the high cost, most practical systems are not going to pay this higher cost to deal with. Okay? So it is used in only situations where you actually are willing to pay that cost. Okay? But most other systems might say it's fine to just deal with crash fault tolerance. We are not going to deal with Byzantine fault tolerance. Is that clear? Any questions on this? Okay, so dealing with so as I was mentioning, detecting that a process is faulty is easier. You just need 2k plus 1, which means there needs to be 3 processes, as you saw here, to detect that something is wrong. Okay, but you can't recover from it or reach agreement. For that, you need 3k plus 1 or 2/3 majority. Okay, in some sense. Okay. Now, there's a lot of work on Byzantine fault tolerance that has started again, because this is the protocol that is used in things like blockchains. Okay. Because there you are making transactions and you might be using that for things like cryptocurrencies. So you don't want some Byzantine faulty process to put some bad records into your blockchain and cause problems. So in those cases, you actually pay this high price. But in most practical system, your web service, you are not going to put 4 copies typically. Okay? You get away with just saying k plus 1 copies. If you want to even tolerate 2 simultaneous faults, you put a 3rd. Okay? That's it in most cases. Okay? So there are other properties. This is a area that developed this theory that you need 3m plus 1 replicas. People said, oh, it's too expensive, can't do it. So then not much happened for some time. And then once blockchains became popular, this whole area has become really popular. So lots of papers on various kinds of protocols to do this, different assumptions where we assume that all processes can be Byzantine faulty. But what if some processes are Byzantine faulty, but others are maybe more rational? That allows you different properties. So you might say that I trust these copies, but not those other copies in the system. So depending on how you change the assumptions, you can develop different ways to deal with Byzantine fault tolerance or have lesser degree of replication and so on. So all kinds of assumptions have been made that's led to all kinds of protocols, which we will not talk about here. Okay? From our perspective, this is the baseline protocol that should tell you how the Byzantine's general problem works, why you need 3m plus 1. We didn't do a proof. We only showed that for m equals 1, that 4 processes you can do this. Okay? 3 processes you can't do this. So that's kind of an example, not a proof. But that actually there is a proof behind it, which we won't go into here, which says that it is 3m plus 1. Yes, question.
Can we use the concept of topic direction that we have?
Okay. So question is, are we talking about a context where we have a data center that is running some application and you have servers that are producing results that are replicated and you want to agree on which one is right and which one is not, as opposed to the blockchain context, which is slightly different. And the question is, can we use have servers sign the result and then essentially use that as a way to verify the result. The first thing is that as far as the course is concerned, blockchains, web applications, all of them are distributed systems. At the very end of the class, we'll have a short discussion of how blockchains work and so on. Okay, so it's not that we are only focused on web applications. But the question you asked is, can you then produce a result and sign it? Sure, you can produce a result and sign it, but just because you signed the result doesn't mean the result is actually correct, right? You could say it's a database, you send a query, it produces a response, but maybe there is a bug in the database. Okay? Not a malicious bug, just that there is a bug. So the bug is producing garbage output. You can sign the output and send it back, doesn't mean it's right. Okay? So just signing a response, even using a cryptographic signature, which is presumably what you're asking, doesn't mean it's right. It just means that the response came from that entity because you signed it. But you can't trust that the response is right. You can only verify that the entity that sent you is the one it's claiming to be. Okay? It doesn't solve our problem in this case. Yeah, so if you sign messages, you can verify the message actually came from the process. And we'll get to digital signatures and so on in a few lectures, which will exactly address that problem. But you can't verify that the response is right. You can just verify the response came from that entity, is not someone else masquerading as that entity. That's all you can verify. Okay? So we are not yet in the world of security where you can have replicas masquerade as some other replica. That's security. That's not fault tolerance. We'll get to security. Any other questions? Okay. All right. So that was Byzantine fault tolerance. We'll get back to some of these ideas when we talk about consensus next time. But for today, I'm going to focus on part 2, which was going to be communication, specifically reliable communication. Okay, we know how to do one-to-one communication. Okay, that's essentially you can use TCP. The transport protocol detects lost packets, it acknowledges packets and things of that sort. So that's a networking topic. We are not going to get into that. Yeah, but we did talk about RPC semantics when there's a failure back in lecture 3. If you remember, we said client, the server may be down, client cannot contact the server, the message, the RPC message may get lost. Okay? The server may have received the message, it crashes after receiving the message. Or it may produce a reply, but the reply gets lost, or you sent a RPC request, client crashes. Okay? We talked about all of this in terms of techniques like incarnation, gentle incarnation, epochs, okay, then sending, having expiration times for messages and so on. Okay? Just a recap, I'm not going to go back to that discussion. Okay, just go back to lecture 3 if you want to think about network failures and RPC semantics in the presence of failures. Okay? Instead, what we'll talk about here is one-to-many communication. Okay? Essentially, in this case, you have one sender, many receivers, as opposed to one-to-one. Okay? One-to-one, you have one sender, one receiver. Okay? You have a client and you have a server. Okay? That's essentially point-to-point communication. Okay? Here, you are looking at a different scenario, which is called group communication. You send one message, okay, and that message goes to an entire group of recipient, not one recipient, goes to a group of recipient. Okay. So that technique is called multicast. Okay. Multicast is different from broadcast. Broadcast says send a message to all nodes in the network. Okay. That's called broadcast. Multicast essentially says send my message to some subset of the nodes in the system. Okay. Unicast essentially says send my message to one other node in the system. Unicast is what we've been assuming so far. Okay. Now we can talk about multicast a little bit, and then you will see why it actually matters in a distributed system. Okay. So here we have an example where there's one sender and 4 receivers. Okay. And we want to make this reliable, which means the sender is going to send a message, okay, and you want to know if all the receivers received it or not. Okay. Our straightforward approach is let's use acknowledgements. That's what TCP does. Okay. Why can't we generalize that and say sender sends a message, all the receivers must send an acknowledgement. Okay. If some receiver does not send an acknowledgement, you say that receiver didn't receive it, you can retransmit it to that receiver. Okay. Simple approach, acknowledgement based approach. Okay. Works fine, works for TCP. There's no reason it shouldn't work for multicast. Okay. The only problem with this approach is that you are going to essentially get n acknowledgements for every send, where n is the number of receivers in the multicast group. Okay. You send one message, you have to wait for n messages to come back. Those are acknowledgement messages. Okay. What if n is large? Okay. Maybe you have 10,000 receivers. They're all listening. Maybe this is a sports webcast. Okay. You essentially are transmitting and or the internet. There are 10,000 receivers tuned in. Every time you send a packet, you have to wait for 10,000. Okay. Or maybe there are 100,000 receivers. It can happen for popular event. The number of receivers can be very large. So for every send, you have to get n acknowledgements, which can be problematic if n is very large. Okay. Problematic in the sense of the message processing delays at the sender. Okay. Not delays, overheads at the sender keep growing as the number of receivers in the group keeps growing. Okay. This is not a problem in unicast because every send gets you one acknowledgement. That's okay. Okay. Even for smaller groups, you can receive n messages, not a big problem. But as the group size increases, this is not going to scale well. Okay. So what can we do in this case? Okay. That's shown in this picture here, where you see that the sender sent something and you can see there are 4 acknowledgements coming back and so on. Okay, so what is the alternative approach that might work better? Okay, so one way to think about it is an acknowledgement tells you whether the message was received or not. So the sender tells you that. Okay. You can flip it and say, if you received the message, don't bother telling me. But if you didn't receive a message, then you can tell me. That's called a negative acknowledgement or a NAC. Okay. ACK is an acknowledgement. So you can turn this into a negative acknowledgement scheme, which says that only tell me when a message is not received. Okay. Now, how do you know a message is not received? You have to essentially receive the message after the one it missed. So you assume that every message has a sequence number. Okay, so in message number 1, message number 2, message number 3. If you have a receiver, you received 3, okay, and after a while you received 5. Okay. Now you know 4 is missing because you didn't receive it. Then you can send a negative acknowledgement for 4, saying I didn't receive 4. Okay. And then you will get a copy of 4 from either the sender or whoever else is dealing with retransmissions. Okay. This is going to scale better in a large system because we assume that if the network is generally behaving well, okay, only a small fraction of your messages are going to be lost for any number of reasons. There may be congestion in the network, some node is probably corrupted, it's going forward your message, etc., etc. Okay, so you will have a NAC-based scheme where you can see messages arriving with sequence numbers. You see a missed message, you send a negative acknowledgement, and that message is retransmitted. Okay, so now you don't need to worry about n messages for every send. You get only a small fraction of negative acknowledgements, which are the messages that did not get to the receivers. Okay, of course, this is not going to work well if you have a highly lossy network. Because in a highly lossy network, the number of NACs are also going to grow. So because most of the messages are not getting delivered, the network is very noisy. Okay, then you are back to the same problem. Okay, then you may as well have just done the acknowledgement. Okay, but for most networks that are behaving well, have occasional problems, a NAC-based scheme is much more scalable than you do when you have multicast groups with large number of receivers. Is this clear? Any questions on this? Yes. Yeah. The question is NAC-based scheme part of TCP protocol? Is it application-based? So first of all, there is a you can ask that question of multicast itself. Is multicast something you support at the TCP level or higher level? Okay, so there is actually two versions of multicast. There's one called IP multicast, where IP actually has multicast capabilities. You have a IP address that's a group address, not a specific machine address. If you send a message to that group address, which looks like an IP address, but it's a group, and all the messages, all the group receives, the entire group receives the message. Okay, that's done at an application, network level. You also have something called application level multicast, where you essentially have applications implementing this scheme, not TCP/IP, is implemented at an application level. There are both flavors of multicast available. Okay, now specifically to NAC-based scheme, this is done mostly at an application level because there's no concept of this in TCP/IP or anything like that. Okay, can it be implemented on top of UDP? You can implement it on top of UDP. Application level multicast essentially is implemented internally as n unicast messages. You have an library where you do a send to the library. The library knows the set of receivers and it's sending n messages. Okay, so yes, you can use UDP or you can actually use TCP. It doesn't really matter. Okay, if you're doing network level, then you are actually doing one send on your socket. Okay, you open a multicast socket, not a unicast socket. You do one send, and then it goes to n receivers. Okay, so that's different from doing it at an application level. Okay, most of these, okay, you will use something like UDP, but some of them also use TCP. Okay, question is, how do you know you are going to receive a packet in the first place? So multicast communication is not very different from unicast communication. Okay, if you remember, all of you now know how to do socket communication, right? You open a socket, okay, you bind that socket to some port, you listen to the socket on the other end, and so on. So same is true here. Okay, you essentially have a multicast group. Okay, each receiver has to join the multicast group by creating a multicast socket and joining the group. Okay, once you join the group, you can listen for messages, just as you would normally listen for messages on a TCP/IP socket. So these receivers have actually constructed a channel to the sender, and they're receiving messages, or they're waiting to receive messages. Okay, so it's not like this message just suddenly arrived, right? So you are actually part of some application or protocol where you are expecting these messages. Okay, any other questions? Okay, question, is it like a pub sub architecture? So this is you not exactly publish subscribe. We will get to that. This is essentially something more lower level than publish subscribe. This is more of a send and receive abstraction that generalizes our socket abstraction. Okay, socket abstraction by default is unicast, is one-to-one. Okay, there are two entities that are communicating. Okay, here there is a group communicating. Okay, so you can assume that you're part of a group. You can do a send on your group socket and it goes to everyone else in the group. Okay, so it's group communication as opposed to one-to-one communication. Now you can build things like publish subscribe on top of this. Okay, but this is just a communication protocol. It's not something higher level than that. Okay, all right. So there are many ways to think about multicast or broadcast. Essentially, you might say if I send two messages or two of the members in the group send messages, in what order is it going to be delivered and things like that. And this matters because we'll get to this problem of distributed commit and so on in just a second. But FIFO broadcast essentially says that all of the messages from each sender are delivered in the same order. There's no reordering. If I send message 1 and then message 2, everyone else gets message 1 and then followed by message 2. There's no reordering. Okay? This is important because if you're using something like UDP underneath, UDP does not give you that guarantee. Okay? In UDP, you can send two messages. They may arrive out of order at the recipient. Okay? So if you want to now get back some message ordering properties, you have to essentially say that whatever your multicast library is gives you FIFO broadcast, or it might give you totally ordered broadcast. We know some notion of what total ordering is from our Lamport's clock discussion. So you can assume that messages are being sent to this multicast group. They have to be totally ordered in terms of the happened before relationship. Okay? So that's a much stricter version of ordering. You can have causal ordering, which says if send of message M1 happened before send of message M2 on two different processes, then the receive will also be in that order. If message M1 was sent before M2, and before in the sense of happened before, and the receive also is in that order. Okay? That's eventually causally ordered. Okay? There are many variants of this. Okay? There's something called state machine replication, which I will actually talk about next time when I talk about consensus, that uses some of these ideas, but we'll hold off on understanding how that does it. But here is an example of how you can now build higher level primitives that are more useful to us in distributed systems. Okay? Multicasting is a networking primitive. We haven't talked about how we can use this in a distributed system. Here is one primitive that you can build with multicast. It's called atomic multicast. Okay? So atomic multicast, as the name atomic suggests, is an all or nothing guarantee. Okay? You send a message, okay? It's either received by everyone in the group or no one in the group, which means that if someone in the group does not receive the message, okay, and you cannot deliver it before machine crashed or something like that, you undo the receive at everyone else. Because now you cannot deliver the message to a subset of the group. Okay? So it's all or nothing. Okay? Now this might be useful in other contexts, like we have a distributed database. Okay? You want to send a query or a transaction to the database saying, okay, go deduct $5 from this account. Okay? You want that message to go to all of your replicas so that all of them perform that operation. Okay? Or you don't want any of them. It can't be that 3 replicas did it and 2 never received the message. So now all your replicas have gone out of sync. Okay? So atomic multicast is a powerful higher level primitive where you can send one message to a group and it guarantees that either everyone receives it or no one receives it. Okay? Which means if some subset of them has received it and you can't deliver it to some others, then you have to undo the ones that have actually gotten it. Okay? Which means it was delivered to that machine, not yet processed by the application. You cannot deliver it and have the application process it and undo it, but at the multicast library, you can undo it. Okay? So some of this is related to how can you detect that the process has crashed, and then how can you undo the delivery of the message. Okay? So this is done using what is called a group view. Okay? So the group view is essentially the group of processes that are currently up. Okay, initially it's all n nodes in the group. Okay, and then you're sending messages, and what you're trying to do is you're going to see if there's a change in the group membership, which means is there a failure in the group? There's a failure in the group, then there's a chance that your message has actually not been delivered. Okay, because you sent it, some nodes received it, some other process crashed, and then that node did not receive it. Then you have to essentially go for the nothing case because you're guaranteed to the application that it's all or nothing. Okay? So this whole problem boils down to I need to detect when failures are occurring in the group, and which is essentially the problem of a group view change. The view of that group has changed, which means that some nodes have disappeared from the group. Okay? So there's a picture here which essentially shows that you are sending, there are 4 processes, they're sending these messages. Initially, everything is fine. The group is P1, P2, P3, P4. Okay? At some point in time, P3 is actually crashed. Okay? So the system detects that the group of processes that are currently functional has changed. It's P1, P2, P4. Okay? So this essentially means that any messages that are in transit at this point, okay, essentially should not be delivered, because then you have a case where you have delivered it to some subset of the group, but not P3, okay, because P3 disappeared. Okay? So in that case, those messages, even if they were delivered to some subset, have to be undone, and you have to tell the application message can't be delivered. Okay? Failed. The delivery is failed. Okay? Then eventually maybe the system says, okay, fine, we can continue with a smaller group, and then new messages can be sent. Now it's delivered to a smaller group, but the application knows that some replica is down and it needs to do something about it. Okay? So this whole notion of atomic multicast requires that you need to detect when failures occur, and when the failure occurs, anything that is in the process of being sent, you have to ensure that those messages are dealt with carefully. But if there's no failure in the system, everything is good, then you don't need to worry about it. Then messages that are sent are automatically received by everyone. Okay? So note that in this case, we are not worried about network problems. We are worried about processes failing. Okay? The network failed, that's a different problem altogether, because then also some messages cannot be delivered. Okay? So you have a network, you can have a network partition and have the processes disappear. Okay? Because you just can't reach them. The network is essentially partitioned into 2. Okay? Those problems are also an issue. But here right now we are just dealing with processes failing. Okay? So here's an example of a system that implemented this. This was developed at Cornell. It implemented what was called virtual synchrony. Essentially, that's a way of doing atomic multicast. Okay, the name of the system, unfortunately, is called ISIS, not used anymore, but this was back in the 80s or 90s. Okay? So this is the system that developed some of these ideas of atomic multicast, and how do you do this for distributed systems, and how can you use that as a primitive to build reliability, okay? Make sure messages are received and so on. Okay? I won't go into the details of this, but I just wanted to mention that this is where some of these ideas came from. Okay? Now, what I do want to say is that multicast, although I described this as a group communication primitive, there are many different semantics that can be provided by a multicast system that might be useful to higher level applications. Okay? And that has to do with what kind of message ordering you get, or there's total ordering and so on. And here is just an example. We didn't go into all of these. It is just an example of 6 different flavors of multicast. Okay, reliable multicast says that every message is essentially delivered. FIFO, so just delivered, doesn't say anything about ordering. Okay? You send a message, it's going to be received. FIFO multicast says not only is it delivered, messages that are sent by each entity is delivered in that order. When A sends 1 and then 2, everyone else gets 1 and 2 in that order. You are not going to reorder them. Okay? Causal multicast is going to add causal ordering, which means that messages across from other groups, entities are also going to get ordered, not just from a single one. Atomic multicast I just spoke about. Within atomic multicast, you can also give FIFO guarantees and causal guarantees. Okay? So many different flavors give all kinds of different properties. Here we don't want to go into all of these. It's not a class in networking. It's more of a distributed systems class. But I just wanted to explain that there are all of these flavors that you can get into. Okay? All of this is done using application libraries, not network. Okay? Not that you're going to implement this in routers and things like that. Essentially, application libraries or middleware systems that are going to give you these properties. Okay? So we have a few minutes remaining. So I'm going to go into the last part of the lecture, which is distributed commit, and explain what this problem is and how we can address it. Okay? So we talked about atomic multicast, and I said it's an all or nothing property. Okay? Now, atomic multicast is just one example of a more general problem where all processes in the group have to either perform some operation or no process in the group performs that operation. Okay? In case of multicast, the operation was sending a message. Everyone, or sort of rather receive of some message, delivery of the message. So the operation was everybody gets the message or nobody gets the message. But let's generalize that. Okay? Any arbitrary operation you can think of. Okay? Do a query, send a web request. Okay? Either all replicas get it or nobody gets it. Or all replicas process it or nobody processes it. Okay? So that more general problem, you can essentially call it the problem of distributed commit, where you have all or nothing operations in a group of processes. Okay? Everyone has to agree or nobody agrees. Okay? So we'll look at two ways to do this. One is called two-phase commit or 2PC. The other is three-phase commit. Okay? This has nothing to do with two-phase locking. We talked about that as a way to essentially do distributed transactions. Okay? Two-phase locking, completely different concept from two-phase commit. Here we just want to agree on an operation. What the operation is not important. Okay? What we are going to do is we have all the replicas perform the operation, and then we want to get some agreement saying, did everyone perform the operation? If you say yes, then say, okay, it was done by everyone. If someone says, no, I didn't do it, then you're going to abort that operation. Okay? Similar to transaction. Okay? But now the operation is more general. It's not a database transaction. It can be any operation that you want. Okay? And we want protocols by which we have agreement that either everyone did it, or if not, you undo it and say nobody did. Okay? So you want to perform that operation in an atomic fashion across a group of processes. Okay? So it's atomicity across groups, not inside a piece of code and so on. Okay? So we'll start with a simple protocol called two-phase commit. Okay? This is a voting-based protocol. And then we'll generalize, not generalize, but look at a variant of it called three-phase commit. Okay? So two-phase commit is a straightforward voting-based protocol where you have a group of processes, they choose a coordinator. Okay? And this group performs an operation. Okay? The coordinator essentially asks all the processes saying, did the operations take place successfully or not? Okay? So all of these processes have to say yes or no. Okay? Yes means they performed the operation. No means the operation failed or they didn't perform the operation. Okay? If you get a yes vote from everyone, you say commit, which means that the operation has been done. Okay? If you get a no vote from anyone, okay, that's like a veto. Okay? Then you have to tell everyone saying undo that operation. Didn't work. Okay? So because it's an all or nothing, you can't have some subset saying I did the operation, others saying no. So essentially you want to vote and tell everyone saying yes, fine to go ahead and commit, or say no, undo that operation because some processes haven't finished. Okay? That's the basic idea. That's what we want to do. And the protocol works exactly like I described it. There's a coordinator, okay, process, and then there are n processes. In the voting phase, the coordinator asks everyone to vote. Okay? The vote is yes or no. In this case, it's commit or abort. Okay? If everyone votes and then waits for the result. Okay? And so that's in phase one, you vote. In phase two, you decide what happened to the vote. Okay? So you vote, you wait for the result, and then you're going to be told commit or abort. If you say commit, then everyone is going to commit. You say abort. If anyone says abort, the coordinator will send you an abort message, and then you're going to undo that operation. Okay? So that's shown in this very simple two figures here, which is state transition diagram. Okay? So there are 4 states here. Init states is when you start the voting process. Okay, there's a wait state, then there's a two final states, abort and commit. Okay, so initially the coordinator is going to ask everyone to vote. Okay, and then everyone is, so that's the coordinator, and these are each of the processes. So each processes are going to vote. Either you vote for a commit or you vote for an abort, and then you essentially go to the ready state. Okay, and then the ready state is where you are waiting to hear back from the coordinator. So the coordinator, once it has asked everyone, is waiting for responses, and then based on the response, it's either going to tell everyone to commit or it's going to tell everyone to abort, depending on what the vote is. Okay? So if the coordinator tells you to commit, then you go from the ready state to the commit state. The coordinator tells you the abort, you go from the commit state to the abort state. Okay? So the way to understand this is a two-phase process. There's a voting phase where the coordinator asks everyone to vote, gathers that vote. In the second phase, it distributes the result of the vote as either a commit or an abort. Commit means everybody said yes. Abort means at least one said no. Okay, is that clear? Okay, so seems simple, but actually hard to analyze because you have to prove that no matter where or who fails, you are going to get all or nothing property. Right? So because we said any process can crash, they can also crash during the voting, not just before. Okay? So a process might have voted something and crashed. Okay? Or the coordinator can crash. Anything can happen, yet we want to ensure that nothing bad is going to happen. Nothing bad essentially in this case means that some processes have committed and others have aborted. That's bad. Because then some are trying to undo it, something the operation has succeeded. Don't want that. Want all or nothing always. Okay. So the way you are going to do this is you got to then analyze every possibility. You say, okay, maybe I asked for the vote. Okay. The request for voting went out, and then some process never responded. Okay. So I only hear from some subset of the process. What do you do? Okay. The vote is not complete. Okay. Or processes responded, okay, but then before you send back the result, some process crashed. Okay. So then you can't relay the result of the vote to every process. You can only tell the result of the vote to a subset of the process. Okay. Or you essentially have a scenario where you send the vote, you got back the result from the coordinator, but before you can actually commit or abort, actually take action, you crash. So you heard back on the vote, but you crashed before. Okay. So any arbitrary thing can go wrong, and you want to analyze this protocol and say that in any of those scenarios, you will still be in a safe state, which means that you can either ensure that everybody commits, or if some process crashed and then came back up, you can move it to a safe state. Okay, because if it has crashed, while it is crashed, you can't do anything. But when it wakes up again, it will be in some partial state. You can get it to either the right decision of commit and abort. Okay. Now analyzing that is actually not a trivial process. I am not going to do this today because we have only 2 minutes remaining. But next time, I'll give you a quick analysis of how we can look at this very simple protocol and try to convince ourselves that yes, under some scenarios, we can get the system to a safe state. But then we'll find out there's at least one case where the coordinator crashes. Okay, the other processes don't know what to do. Okay? Because you won't actually hear back on the result of the vote. You can't unilaterally make a decision without the coordinator, so we can't figure out what to do. And that will lead us to a three-phase commit, which can tolerate not just process crashes, but also coordinator crashes, and then make sure that you can get this all or nothing property. Okay, but for today, let's end it here because that's going to take a few minutes before we get there. But there's one last question. Yes. Okay. The question is, why is there an arrow from init to abort? I was going to talk about that next time. So this is a case where there's a process that was asked for a vote and it voted for an abort. Okay. If you vote for an abort, you know where everyone is going to land because that's like a veto. So you don't actually have to wait for the results of the vote to be announced because you can locally go to abort. Okay. Others have to wait because they don't know what has been voted. But if you vote for abort, then you know what the decision. If you vote for commit, you don't know the decisions of the vote because you have to ensure that everyone else committed before you can decide whether you go here, or if anyone else aborts, then you end up there. But if that process votes for an abort, then the decision is known to that process, not to the other side. So that one can make a direct transition. Okay. Good question. Yes, question. Okay. Question is, are these multicast techniques used for consistency? The multicast techniques are used to ensure some variation of variant, not of correctness as opposed to consistency. To get consistency, you need to do more than just multicast, right? That is why we are talking about distributed commit, where that's basically it has to get yes, all or nothing property. You might need something like atomicity or other things on top of it. Multicast is just delivering a message, not doing anything more than that. How you process the message, what do you do after that? That is where you need all these additional techniques to get us to a good state. Okay. So multicast by itself is a pure networking technique. It just delivers messages. That is not something you can use to get higher level properties. You need to do more. Yes. So the multicast is our base level communication primitive. On top of that, you want to give atomicity. This is one way to do it, right? So, and then we may need to do more things beyond that, which is recovery and things of that sort. All right. Okay. So we'll stop here, continue next time.